So welcome to today's Plan Talk. Today we have Hattie Zhou with us. She is a PhD student at University of Montreal and Mila, and she is currently also still interning at Apple and has worked as a student researcher also at Google Brain. And today she will present her paper, What Algorithms Can Transformers Learn? A Study on Length Generalization, which was also accepted to LCLR this year. So thank you for joining us, and you can take it from here.
Great. Yeah, thanks a lot for having me. I'm really excited to be here, and I am happy to take any questions or discussions or comments as we go. So please feel free to interrupt me. So yeah, some motivation for this line of study. We've all seen a lot of really interesting generalization behavior in these large language models. For example, GPT-4 can draw a unicorn in ticks. These models can solve math problems or be prompted to learn new skills from in-context learning. And there seems to be some interesting generalization happening that we don't quite know how to formalize. And it's really hard to study these models and these variety of tasks because they're hard to control. And how do we measure how well the model is drawing unicorn ticks? That's difficult to quantify. And also, it's hard to do ablation on models of the scale since they're very expensive to train. So in this work, we try to focus on a particular mechanism for generalization and try to study them in more synthetic settings. So the question we focus on here is to ask, can transformer models learn algorithms from just training on data? And transformer models are, the foundation of a lot of these language models. And one form of generalization, especially on algorithmic tasks, is for the model to learn the actual underlying algorithm. So to look at this, we focus on synthetic, simple algorithmic tasks like addition and sorting. And we train models from scratch to convergence on these tasks. And we train them on a certain length and evaluate them on outer distribution settings, which are longer length. So for example, for addition, we might train on problems of up to 3 digits and then evaluate them on 5 digits. And this is often referred to as length generalization. And it's a good proxy for checking if the model has learned a solution that could generalize. And length is especially challenging because you're asking the model to generalize to harder questions most of the time. So generalizing to harder tasks can be a proxy for whether the model has learned the underlying algorithm. And length generalization has been pretty commonly studied in the literature, and some examples are listed here. So transformer models tend to perform very poorly in these evaluations. For example, a paper from Anil et al. Looked at either fine-tuning or training from scratch or training with Scratchpad on some simple tasks like parity or variable assignment. And the gray band here is the length that they trained the model on. And we can see the performance degrades as soon as the model goes out of distribution. And this is pretty normal behavior to observe in a lot of the previous work. And so we wondered, are these models even capable of learning something that would less generalize? Can we find some successful settings for this? And one setting we found is the counting task. So here you're given 2 integers A and B, and the task is to output the sequence from A to B. So for example, you have a prompt here, 5, 8, and the output you want the model to learn is 5, 6, 7, 8, followed by an end of sequence type token. So if we train models on length of up to 60, meaning that the gap between these two numbers is at most 60, and then test them on length up to 100, we find that the model actually performs perfectly on this setting. And this is quite surprising because the model has never seen or had to output a sequence of this length. And so it's suggests that the model is learning something that's length agnostic. So now the question is, why do these models generalize on some tasks but not others? So clearly these models are capable of some sort of a pretty extreme out of distribution generalization. And can we understand when they're likely to have that ability and where they're not, and try to understand them from the perspective of the task that we're evaluating on? So going back to the counting example, let's think about how this might possibly work. And one observation that we can start with is that we can notice a transformer model architecture is running the same program for any length. So we have a context window, the model is processing every location of that sequence. And so for a shorter sequence, like on the left here, the model is predicting the next token in the sequence. And this very same model is being applied to a longer sequence on the right, predicting the next token for a longer sequence. This is kind of similar to how we might run a computer program on any type of or any length of input. So it's nice that the transformer model architecture is kind of designed to work for all parts of the context. Okay, and the second observation here is that the counting task can be solved by an algorithm that would work for any length. And the algorithm can be really simple. One possible algorithm is to just look at the previous token, see if the previous token you've outputted matches the ending token that you want. In this case, the ending token would be 8. If it matches the ending token, output the end of sequence. Otherwise, just increment the previous one by 1. And so if the transformer model somehow learns this program when trained on shorter sequences, then we can expect it to length generalize on longer sequences. And it turns out that this particular algorithm can be represented by the transformer uniformly for all lengths. And so it is possible to construct a set of weights for a transformer model that actually implement this algorithm. And moreover, this construction is simple. And so we might expect it to be plausibly learnable also during a training process. And so some intuition that we can build on then is to think about whether the algorithms that we're trying to learn is one that's actually simple to represent by the transformer architecture. And if it is, then we might expect it to also be easy to learn if something that's very simple to represent. And if it's very difficult to represent, we might expect it to be harder to learn. So that's kind of the intuition that we build on and that we try to evaluate empirically. So the hard part to testing this intuition is how do we define what is simple to represent for the transformer architecture? In the previous example, one way to do it is we can manually construct weights, and a lot of papers have taken this approach, but this is very tedious and it's very difficult to scale because we have to analyze every single task separately. And it doesn't really give us a lot of general intuition for what is simple to represent. And so one other way that we propose to do this is to build upon the RASP programming language, which I think maybe many people here are already familiar. But I'll give a simple introduction as well. But this is, oh yeah, so the RASP language is essentially a domain-specific programming language that's tailored to the transformer's unique information flow. And every operation you write in this programming language can be directly compiled to an actual layer in the transformer model. And we can kind of realize this as just a restricted set of Python operations. So to think about what kind of algorithms is simple to represent, or at least possible to represent in a transformer, we can try to write out that algorithm in terms of RASP. And some intuition for what the RASP language tries to capture. It only allows parallelizable operations, and this matches with the transformer because the transformer model is an inherently parallel model of computation. It only allows sequence to sequence operations, so everything has to take in a sequence, an input sequence, and an output sequence of the same dimension. And we don't allow arbitrary loops or control flow, which we can't really do also in a transformer model. And we considered a case which uses causal masking to study the more common decoder-only type models. And the main operations are sequence map and KQV, which can be mapped to MLP and a tension layer, respectively. And to kind of leverage RASP for our purposes, which is to look at what normal trained transformers are likely to learn, we also introduce a variant called RASP-L, which kind of accounts for a couple quirks of normal transformers for the purpose of learning length generalizing algorithms. And so a couple changes here, we limit all the variables to be bounded integers to not run into any numerical precision issues. And we don't allow arbitrary operations on index information. So that's things like saying, give me the token that has an index value that's half of my current index value, or something, some type of operation on index information. We don't allow because it's hard to even think about how would we construct a way to represent positional information that would allow arbitrary kind of arithmetic operations on it that would generalize. And I'll talk more about this with some specific examples that we can look at. But this is another change that we make. And we also allow min and max aggregations in the KQV function, which is just a simple extension to what RASP already does. Maybe I'll pause here for a second and see if there's any questions or comments. Is this all making sense so far? Okay, great. So now, armed with this RASP-L language, we can formalize our intuition a bit more and propose this toy model. which is that for symbolic tasks, transformer models tend to learn the shortest RASP-L program that fits the training set. This is, of course, a very strong statement. We don't expect it to be absolutely true, but I think it's a very interesting toy model to think about. And it is reminiscent of kind of minimum description length type of ideas, but specific to the transformer model, because now we're using a measure of complexity that's kind of designed for the transformer. And the measure of complexity here is can be thought of as maybe the length of a RASP-L program that we can write, or the length of the simplest one that we can write, which is not always easy to come up with, but that's how we can think about it conceptually. Okay, so let's look at an example of what a program for a task in RASP-L might look like. So here we are giving the RASP-L program code for that counting algorithm that I described previously on the right. And then on the left, we just have an illustration of how we're going from input to output at the bottom, and the intermediate results that correspond to each of these operations. Are people really familiar with RASP here? I'm just curious. Is this already a pretty, maybe some? Okay, it seems like, okay, I'll give some maybe just quick intuition. I won't spend too much time here, but yeah, for anyone who's maybe forgotten or not super familiar, yeah, so like I mentioned, there's two main operations. One of them is KQV, which essentially computes like an attention operation. And for KQV, we define a mask that is like a matrix, which which has the dimension of your key and query, and then a value that you want to aggregate based on whether the mask value corresponding to the index is 1 or 0, essentially. And so, one way, okay, so for this first operation, we're trying to find the start index of a sequence, which is we're trying to find the location of this start of sequence token, so we know where to look at to find our prompt. And we can do that just by comparing the input values to a sequence of the start sequence token and see where that matches up, at which position that matches up, and then compute or essentially select that value. So the value here is the index value of our sequence, and the mask here is generated by comparing the input to an starter sequence token. Yeah, and we can kind of visualize this with the mask and then aggregation over this mask. We only find one starter sequence token here, so there's only one column, and this only starts after or at the third position, essentially. So we're just returning the index value of the starter sequence token when we can find it. And one thing to note here is that we have this causal masking constraint. So all the mask, or all the keys and queries can only compare to tokens that came previously. And this is actually quite restrictive in a lot of cases as you try to write algorithms in RASP-L. So this is something to keep in mind. So I'll just maybe skip that. sequence map essentially takes two sequences, performs an element-wise operation on them, and then returns the result. So yeah, maybe I'll not spend too much time here. And one thing to know is we can construct pretty complex operations by just using these elementary operations like sequence map. So here we write a version of the where function that's equivalent to the NumPy version of where, and just using the sequence map functions that we talked about before. Okay, so anyway, so this is what we can do for the counting task. And yeah, so now let's talk about the main conjecture from the paper, which is a more testable version of the toy model that give us some intuition. So we hypothesized that a decoder-only autoregressive transformer is likely to length generalize on a symbolic task if the following conditions hold. First, the true algorithm that we're hoping to learn must be possible to represent by a transformer. And second, this representation should be relatively simple. For example, it should have a short RASP-L program, because if it's complex, it may not be preferentially learned. And that's kind of what we try to capture in the third criteria, which is that the training data for this task should be diverse enough such that there is no shorter RASP-L program that fits the training data, but not the test data. And this is just kind of trying to capture the idea that you shouldn't have shortcut programs that exist in your training set. And you can consider shortcut programs as shorter RASP-L programs that do not generalize, essentially. So this is the main thing that we want to test in the rest of the work and in the rest of the presentation. But if this is true, this gives us a good way to predict for any task whether a transform model is likely to generalize or not, whether the target algorithm is likely to be learned by a model or not. So to test this, we have a set of tasks that we come up with that either has these RASP-L representations for the true algorithm or it does not. So on the left side of this table, we have a set of tasks that we can provide RASP-L solutions to. And on the right is a set that we cannot, and we can discuss maybe some intuitions for why. But the question is, does the existence of the RASP-L programs help us predict generalization performance on these tasks? So the counting task, like I described before, I said, does length generalize? And here's a closer look at what the performance looks like. So we can train models for up to different length. So the different lines here represent models trained with a maximum length of 10, for example, for this yellow line, and the highest is length 80. So this is just saying during training, how long can the sequences be? And this can be thought of as actually a proxy of the amount of data diversity that we're giving the model during training. So remember in our hypothesis, if the data is not diverse enough, then it's more likely that there are shorter RASP-L programs that can fit the training data but not generalize. And so here we're trying to see what the impact of diversity looks like. And on the x-axis here, we're showing the length that is so 10 over the maximum training length for each of these models. So for the yellow line, the x-axis 10 here would represent test length of 20, but for the next one, it would represent text length of 40 or 30 and 40 and so on. And so, yeah, so the y-axis, we're showing test performance, test exact match, meaning that the entire output sequence is correct. So we can see here that with low train diversity, meaning low maximum training length, the models show relatively weak length generalization. Starts to degrade pretty rapidly. But for models with pretty high training diversity, we're seeing pretty strong generalization. So for these last few lines, models are trained with length 60, 70, and 80. We're seeing them generalize to length 100 to like 150. Okay, now let's look at a different task. And here the task is mode, or finding the most frequent element in the sequence. And an interesting note here is that the task now defines length in terms of the input, whereas the previous task defines length in terms of the output. And here, given a sequence, we want to output the token that was the most frequent. And there is a unique answer for all of these examples. So yeah, similarly, we look at models trained on different lengths, and we see pretty strong length generalization as well. They're not perfect. They do degrade over length, and there could be many reasons for that. But here, all the models at least generalize to 10 more than what it has seen in training. And this is materially different from most of the prior work that looked at length generalization, which, if you recall from the very beginning plot, those models tend to degrade as soon as you go even 1 or 2 length out of the training distribution. So we are seeing very different qualitative behavior for these tasks. And it's also interesting to know that the curves for this task are different. Like the training data diversity doesn't seem to affect things as much as it did for the counting task. Okay, now let's look at 2 versions of the copy task. So the copy task essentially tries to repeat what you're given in the prompt. And on the left, we have a version where every single token in the prompt is unique by design. And then on the right, we have a version where there are only 2 possible tokens. They're arranged in a specific order, and you're supposed to copy or repeat that order. So on the right, we only have tokens A or B, and they're kind of given a certain combination. So if we analyze this task using RASP-L, on the left, for the unique tokens task, we can see that there is an easy solution, which is we can use something called induction head. Induction head essentially looks at your previous tokens, find a match for the current token you're looking at, and then copy whatever came next to the previous instance of your token. And this was introduced in some mechanistic interpretability work and proposed as a potential mechanism for how in-context learning might work. And using RASP-L, we can actually show that an induction head is very simple to write in this language. So with unique tokens, we can use induction head to just look at where we are in the sequence by finding a match and then just copy whatever came next. So this should be quite easy, but we can't really do that with tokens that have repeat values because it would no longer be a unique lookup. So that would be more difficult. And what we might have to do then is to figure out which position or index we are, and then try to copy the next one. And this is much harder. And we can kind of see this reflected in the performance as well. So on this plot, we're showing test performance at length 50 for models trained on different maximum training length. So it's kind of the same setup as before, but we're plotting it a little differently now. We're trying to see what amount of training length it would take for the model to generalize at length 50, if it ever does. And we can see for unique tokens, models start to generalize really well, would train on sequences of 40. But for the repeat tokens, no matter how much we train on, it does not generalize to length 50. And this is consistent with our prediction. So maybe pause here again in case there's any questions. All right, so now we've seen the examples that we predicted should be easy for a transformer. And indeed, we do see that these models at least show non-trivial length generalization on these tasks. And then now let's look at a couple of tasks that have been pretty widely studied and shown to not work in terms of generalization. And one of them is the parity task. The parity task essentially gives you a sequence of zeros and ones, and you want to find whether there's an even or odd number of ones in the sequence. A natural way to do this is to scan your sequence from left to right and just keep track of a state variable for, if we have an even or odd sequence up to that point. And this is very natural to do for a model like an RNN. And if you train an RNN on the parity task, it's pretty easy for it to learn. However, we can't keep track of a state variable with a constant depth transformer because transformers have to do parallel operations for a certain number of times. So that algorithm is very unnatural or not possible to represent for any length. It's easy to learn the parity task for a fixed length, but we can't learn a solution that generalizes to arbitrary length because of the structure of the transformer model. Now, maybe you would wonder, okay, can we come up with a solution to this task that is parallel? Maybe one option is you can calculate the sum of your sequence and then get the parity of that sum. That would be more like a parallel solution. However, getting the parity of a sum, if the sum is greater than a value that the model has ever seen before, if the length of the sequence is much longer, that's not an operation that we can reliably generalize on. Because essentially, the model has to be able to represent a sum of a larger number that it's ever seen, and then know what the parity of that sum should be. And that's very difficult to learn. And so this is kind of giving us some intuition through looking at it from the RASP perspective to try to understand why parity is so difficult for the transformer to learn. And indeed, when we train models on this task, we don't observe any length generalization. And addition is another example that's been pretty widely studied and also do not generalize. And here is where the discussion on the index arithmetic comes in. So to solve addition, the model needs to basically find the correct corresponding digits from each summand at each output step. So to look at the 6, the model wants to index 5 from the second number and 1 from the first number. And this indexing operation is what is actually difficult to represent in RASP-L, or impossible to represent in RASP-L. The actual algorithm itself, the actual summing of values, going from right to left, that's all possible to do. But the hard part is, how do we get the model to figure out which digit it should be looking at? The operation we can think of is something like maybe at index n, give us the value that's at index value n over 2, something like this. But this kind of thing, we can't expect the model to learn in a generalizing way. So if the model has only ever seen sequences of up to length 10, and we expect it to do index operation or index arithmetic on an index value of 20, and then we're asking the model to do 20 divided by 2 when it's only ever seen length of 10. And so this is where we can't, or we don't know how to represent positional information in a way that will allow those operations to be learned in a generalizing way. It's not to say it's not possible, but this is why we prohibit it from RASP-L, because it seems that it's hard to represent. We don't empirically observe that the model can learn these type of things. So yeah, addition also does not generalize. And we think this is where the difficulty comes from. Okay, so now we basically show that for all the tasks in this table, length generalization performance perfectly corresponds to whether or not we can write a RASP-L solution for it. So the next thing we want to consider is, now that we have a better understanding of why certain tasks are difficult, can that inform how we might be able to make some changes and improve generalization performance? And the first lever that our conjecture suggests is, if we can convert the task to one that has a short RASP-L solution, then maybe we can expect the model to generalize. And the second lever is, maybe we can increase our data diversity so as to remove the possibility of shortcut RASP-L programs. And let's see some examples of this applied to the task that we just discussed. So for addition, here is just the baseline performance of, again, in the format that we looked at before, evaluating on length 50 by training on models of varying length of less than 50, and the model essentially do not generalize at all when addition is presented in this format. And this may be because we cannot write a RASP-L solution for it. And that's because we cannot represent this index operation. However, like we looked at before, we can use something called induction head to do indexing pretty easily. So one way to allow that solution to exist for addition is to add these index hints at each location of the digits. So here we're adding index hints A and B to represent the first position of each number, the first digit, and the second digit. And we also output the index hints or index tokens in the answer. So with this augmented format for addition, we no longer need to rely on index arithmetic operations, but rather we can just use induction heads to look up the correct digit. So now we can actually write a RASP-L solution for this task. And so compared to the version with no index hints, we see that if you just add index hints, addition can now generalize, at least way more than what has been seen in prior work. And yeah, in the comparison here. And the dots are just the performance over 20 different runs. So it is interesting to see quite a big spread for when the models are on the cusp of maybe being able to generalize. Okay, yeah. So this is normal addition. However, one other way to simplify this task is by reversing the order of addition. So intuitively, we know that reverse order addition is simpler than forward order. Reverse order just means you're calculating the last digit of the answer first and then going backwards. And this is how we would do addition ourselves as well. And that's because the carries influence potentially the next, or yeah, the more significant digit. If you output things in forward order, you have to essentially, to output the very first digit in your answer, you need to know if there is carry from all other previous digits. And that involves a lot of additional computation than if you did things in reverse order and you can just look at your previous output to see if there was a carry. And indeed, if you try to write the solution of both of these versions of addition in RASP-L, the reverse one has much fewer lines. It's much simpler. And so this, we want to see if, empirically, the model performs similarly to our intuition for what should be easy or hard. So we introduced this reverse variant where basically the prompt is still the same, but we just present the answer in reverse order. And the forward one has longer RASP-L program, the reverse one have a shorter one. And so we see both of these actually generalize in the standard evaluation that we looked at. And by standard evaluation, I mean we're sampling these two numbers independently and randomly. So one issue with this is that in standard evaluation, to get something of this form where you actually rely on a chain of carries to get your answer is almost never happens, essentially. So just imagine like sampling two random numbers, but they must add up to something like, or yeah, imagine getting a number like 73 plus 27. The answer is 100. That's where you have this chain of carries, but that's very rare, especially when you go to longer digits like 45 digits or 50 digits. And so we're not really testing whether the model has actually learned this part of the algorithm with the standard evaluation. So we do something to test that by evaluating on hard carry questions, and that's when there's this chain of carry. And when looking at those test examples, we see now there's a big difference between forward addition on the left and reverse addition, which still is mostly generalizing. So this kind of shows us forward addition actually didn't learn the correct algorithm when we're probing it in this hard case. But like I mentioned before, there is actually a RASP-L solution for forward addition, even though it is much more complicated. And that goes back to the second lever that we considered, which is maybe the data is not diverse enough to squeeze out some potential shortcut solutions for forward order addition. But the fact that one exists suggests that maybe we can make it generalize better if we try harder. Like, it is possible. And one way to do this is simply by sampling more of these hard carry examples during training. So again, we're training on shorter length, but we're seeing some more examples that have this carry train type of behavior. So when we do that, both easy and hard carry questions for addition now show generalization, at least starting from length 40 and being able to generalize to length 50. And this is pretty cool because it's all still very consistent with the behavior that we predicted, which is if the underlying algorithm has short RASP-L program, then it's easier for a model to generalize on that task. And we can also look at just the training behavior. So now we're looking at training exact match for forward and reverse addition. And we can see, even though the format of the two tasks are, seem like they should be the same to a transformer model, the reverse addition is optimizing faster than forward addition, which is quite interesting. It's like the actual relationship is maybe a little bit easier for the model to learn. So yeah, so that's kind of a deep dive on addition. We can also use this perspective to get a better sense of why Scratchpad helps in a lot of reasoning problems. And we can look at that by looking at the parity task. And here we just introduce this new format for parity based on some of our intuition before. So we added index hints like for addition. Also, we added this weird looking scratch pad, which essentially keeps track of either we're in an even or odd state as we process the different index positions. And then we arrive at the final answer, we take that to be our prediction. And the reason we have the scratch pad is one of the intuition for parity not working is that transformers can't keep track of a state variable for constant depth models. And Scratchpad can give us this rudimentary way to do a loop or to keep track of a state. And as we would predict, when you train on parity of this format, a model generalizes very well. Whereas before, it would all be performing at 0 for test length 50. So yeah, once again, it is interesting to see why Scratchpad should be helpful by considering where in the original task a transform model is struggling with. Now, this also means if a Scratchpad is designed such that it is actually resulting in a harder RASP-L program, then we should actually expect the Scratchpad to be harmful. And that is something we can try out with the mode task. So for mode, we already know that a simple solution exists without any Scratchpad. But a human can come in and be like, I want to design the intermediate steps to help me solve this task. And one way to do this is I want to count the occurrences of each token in our sequence. So we get each token, we get the count, and then that can show us which token has the maximum count. And that should be our answer. So here is one version of that Scratchpad. Essentially, we get the count of each token. But actually, This, in terms of RASP-L, is a much harder thing to try to represent. Counting the number of occurrence is not necessarily hard for a transformer, but converting that count internally into a decimal representation in the output requires a pretty difficult conversion that also we don't expect to generalize to counts that are higher than it's ever seen in training. So this scratchpad essentially makes the problem more difficult. And we can see that it does perform much worse. So the blue diamonds here are the performance of the original format, and it was generalizing pretty well. And the orange, or let's look at the green circles, is the performance of getting this total, this entire output correct with the scratch pad, which is more difficult because there are more tokens in the output. So we also looked at this orange square here, which only checks if the model gets the final answer correct. And technically, the model could just ignore the scratch pad and still learn the correct solution for the final answer. It is always in the same position. It is always the same solution as what the blue task saw. But even then, the model is still performing much worse, suggesting that just having this difficult scratch pad can confuse the model, and the model is trying to learn something a little more complicated, and that actually hurts the performance. Okay, so I think that is all the results I wanted to go through. Just a quick summary. We saw that transformer models can indeed generalize to harder instances. It seems to have the capacity to do length generalization, even though it's been shown to be very difficult. And empirically, we've shown that transformer models generalize to longer length if and only if they can represent the true algorithm. And we know when that happens, at least it happens at least when we can represent that true algorithm in terms of RASP or RASP-L. And so the conjecture that we propose is that RASP-L programs can be also learned by a transformer during training. And the consequence of this is we can think of improving length generalization by reformulating tasks in formats that are easier to represent in RASP-L. And okay, whatever. It's yeah, so it helps us predict and understand what kind of tasks are natural and easier to learn and generalize them for a model. And for tasks that don't generalize well, we can try to pull these levers to try to improve performance. So that's all I wanted to talk about. I think maybe we have a couple minutes if there are any final questions.